out. And then we are going to share screen. So maybe I do the whiteboard first today. Because today what we will learn, hold on, we have a student coming in. So what we will learn today is about Hoffman tree. Okay, we have another student. So we will learn Hoffman encoding and decoding algorithm. Okay, so we will take a look what that is, and if you recall, okay, anyone can someone turn off your audio? There's some echoing. So Hoffman tree, okay, and encoding. So here it involves encoding. I need to admit a student. So here it involves encoding and decoding algorithms. Okay, and if you recall that ASCII code, it's just some coding scheme. Is it in computer science, computer engineering? There are all sorts of coding scheme. Is it even with your a cell phone call? Is it also involves some coding scheme? Is it? And with like a JPEG file, is it? Like the image file, audio file, it also involves some coding scheme to do compression, is it? Something like that. So anyway, ASCII code, it's use 8 bits, is it, to represent some English letters, is it, like A to Z, is it, A to Z, and also 0 to 9, is it, plus some a couple a number of other signs on the keyboard, is it? That's called ASCII code, is it? It's use 8-bit, and now with the internet also support Unicode. Is that we always say like UTF-8 or something, is it? And like in computer engineering, like a compression, the CCITT, some kind of compression coding algorithm, is it? So this Hoffman is also kind of some coding algorithm. And for ASCII, it's always use 8 bits, is it? And Hoffman for the plain text, like each letter, is it? For Hoffman, it's not to use fixed length. So it use variable length of 0 and 1s to represent like some letter, okay? Some letter. So that's, it's variable length. So this is different, okay, from like ASCII code. And the idea is suppose like, suppose you have an article or you have a novel, okay? And it has a lot of words, and of course then it has a lot of letters, is it? It's made up of a lot of letters, and each letter's occurrence, the frequency, okay, we say the frequency, hold on, let me get a student. Each letter's frequency of occurrence in that book or that article or a paragraph, something based on what your selection is it? you can always find the frequency, is it? And then based on the frequency, based on this whole book or whole article or whole paragraph, something, is it? Then you can give each letter the frequency weight. And the total weight of all of the letters should be 1. Is it? So some percentage of the weight. Is it? So let's see, suppose over here, we have something looks like this. We have 0.1, we have another 0.1, then we have 0.15, and then we have 0.2, and then we have 0.45. So anyway, so this is the frequency weight. Okay, the weights. And here we have letter B, here we have letter C, and the letter D, and the letter A, and the letter E. Okay, assuming in an article or in some paragraph, and you only have these 5 letters, okay? And these 5 letters, so you can see there are a lot of E occurred in that article or some paragraph. And the second most frequent used letter is A, and come next is D, and B and C are the least frequently used letters in that paragraph or in that article or something. Okay, so you can sort all of the letters unique, okay, all of the letters, the frequency, occurrence frequency in ascending order. In ascending order like this. Okay, and once we have this, then we can start to build, we call it a double tree. We can build a double tree. Okay, so let me clear this part and let's do it again. Okay, so here I will redraw it. It's 0.1 is B, and then we have another 0.1 is C, and another one 0.15 is D, and then we have 0.2 is A, and then we have 0.45. This is E. Okay, so we arrange them in ascending order. Okay, then what I'm going to do, I will use pair by pair to build a double tree. Double tree, okay. So I'm going to add both of this weight together. And what's the weight? We can get 0.2. Okay, so this is kind of like our binary tree, is it? You have a node, then it's left child and right child. Okay, and here, so we are going to add the weight from 2 child nodes together and make it as a new root node. Okay, and then we have this small tree, is it? And at the same time, its left branch we identify as the number 0, and the right branch we identify as number 1. Okay, and then next, so we get this pair done. Then next we are going to pick 0.2 and D together, make it build a tree. Okay, and we add both together, we have 0.35, is it? And same thing, we have 0 here, and the right branch, we write 1. Okay, and then next, what we are going to build is 0.35 and 0.2, okay? We are going to add this together. So it's going to be 0.55, is it? And the left branch is 0, right branch is 1, okay? And we continue with the last one, okay, it's 0.5 and the node is weight. So we have what? If we add both together, we will have 1.0, is it? Then left is 0 and right branch is 1. Okay, and now we build this tree. Okay, so this tree is called a double tree. It's a binary tree, is it? Each node has only 2 branch, is it? So that's why we also put this in this unit, binary search tree unit. Okay? But it's not a binary search tree, okay? We call it a double tree. This is not a binary search tree, okay? It's binary. Of course, it's binary tree, but it's not a binary, so it's called a double tree. It has 2 branch. And you can see when you add all of the weights together, it should be 1. Is it? It should be 1. Okay, and next, then let's take a look. How to get E? Get E is just 1. Is it? You just start at root node. At root. And then follow branch. And arrive at leaf node. And the leaf node has a letter. And along the path, you have either 0 or 1. For E, you only have 1. That's it. And then let's see A. For A, you need to go to 0 and then go to 1. That's it. So A is 0 and then 1. You have A. And someone, can you please turn off your audio? And then let's see D. D, you go with what? 0, 0, and then what? And then go to right. Is it? So 0, 0, 1. Is it? 0, 0, 1. Is it? And then go to D. Is it? And then go to C is what? 0, 0, 0, 1. Then 0, 0, 0, 1. Is it? Then you go, you get C. And for B is all 0. Is it? So you get, so through the path, you can reach each letter. Is each letter. And you can see following the path, you have either 0 or 1. Is it? And basically, all of this they are Hoffman codes. Hoffman codes, okay, for this set of A, B, C, D, E. Okay, just in this case, okay, it's not always like a ASCII code, it's a permanent one, it's never changed. Is that Unicode? It's permanent, it's not changed. But for Hoffman code, it depends on the article or the novel or the book or the paragraph. Is it? Each time it's going to be different, okay? But anyway, in these cases, then we have, okay, letter E is 1, letter A is 0, 1, letter D can be represented with 0, 0, 1, letter C can be represented 0, 0, 0, 1, okay, letter B is represented with all 0, is it? And we can also see all of the codes are variable lengths. Variable lengths, is it? So, but over here, it's not just variable lengths that will suffice. And if you take a look, the pattern of these codes, E is the most frequent letter, is it? So most frequent letter, then it's code length. Code length is what? Is the shortest. Is it? You only has one. Is it? And the least frequent letter, the code length is what? Is the longest. Is the longest. So here for Hoffman codes, the idea is you use shorter.
You got over 3 grams?
Can someone turn off your audio? Use shorter code.
Yeah, I'll take it.
To represent frequent letter. Frequently used letter. And you use the longer codes to represent what? Least less frequently used letter. Is it? That's what the Hoffman variable length here is. And this also good. Is it? Because if some letter appear very frequent, you use them very short. So that kind of saves space. Is it? And if it appears like you use them longer, is it won't take a lot of space? Not like ASCII code or Unicode. No matter how frequent or how rarely you use, it's always the same length, is it? So in this regard,
oh good, I said a screenshot. She goes, oh good, I'm broke.
Oh, can someone?
Brandon, please turn off your microphone.
Who the student let me can you turn off, because I cannot once I will stop the sharing, then the whiteboard is gone. Yeah, so please stop your audio, okay? And where did I the variable length, is it? We explain the benefit regarding this. Is it you use shorter codes to represent frequent. You use a longer code to represent rare use letter. Then in this case, just think about it, can save a lot of space compared with fixed lengths. Is it fixed length? Okay, and if you take another close look, observe more, you will also find there are some other restriction is the shorter one, the shorter code, the shorter code will not be, I cannot write it, will not be prefix code for longer ones. If you take a look here, is it now we don't have 0, is it? There is no 0, because 0 then is going to be prefix for A, D, C, B. So 0 definitely not allowed. Is it not allowed? Can you do 0, 0? No, there is no such thing. Is it because 0, 0 is going to be prefix? So the shorter code, you can also see in this case, will not be the prefix of the longer code. Okay, that's another feature in Hoffman codes. When we build the double tree, it will automatically meet this condition. Okay, so this is the idea of Hoffman codes. So from this Hoffman, the double tree, we build the Hoffman code. And basically, the code also has a feature, we call it can minimize the expected code length. Okay, the way we build the double tree, okay, it achieves the goal to minimize the expected code length because it's a variable, okay, and it will minimize. So that's another feature, okay. Okay, so this is a general idea about Hoffman code. Okay, and then next, let's see. We already see the, we already kind of discussed the concept of Hoffman tree, okay. And so what next, let me give you a table and then let's see if this is workable. Okay, so we have some character. I will have a table. Okay, and then I have the weight. Okay, and I have A, and I have then B, and I have, and then C, then D, then E. Okay, then I have the weight list like this. Okay, and then suppose this one. So here we have character, and then here we have, hold on. Here we have code. Okay, so A, then we said we are going to encode with 0, 1. And the B, we are going to encode something like this. And C, we are going to encode as this. And D, we are going to encode as this. And then E, we are going to encode as 0. So based on the letters frequency weight, is it? Then I said, okay, I generate the following codes. So the question is, does this code meet the definition of Hoffman code? So how about this is our first quiz question. And why yes or why no? The one I'm giving, is this the Hoffman code? Is it's going to be a legitimate Hoffman code over here?
It is not a half code.
Yeah, so it's, yeah, so why?
Because the A is 0, 1, but you mentioned the A maybe is 1, and the last is E is 0, 0, 0.
Yes,
And
yes.
I didn't say in the Hoffman have 1,000 the number. I just saw the 0, 0, 1, 0, 0, 1, but they have 2, 1.
Okay, so let's take a close look. Okay, so if you take a look, E is 0. Is it 0 is what? Prefix of 0, 1. Is it? So it doesn't meet. You cannot do that. Is it? Because later on we will see the reason why it's not. Is it? And also see this 100. Is it not 100? 100, is it? And this 10 is what? It's a prefix of what? Of that 1000. Is it? That's a prefix. Is it? So it doesn't meet the definition of our Hoffman coding. Is it? So this is not. Okay, it's not. Because what? The reason is some of the code are the prefix of the other codes. Okay, so that's the first quiz question. Okay, so we are done with this. And then next, let's see, generally, so how do you come up with the code? Is you need to collect all the single letter. is it? And count how many times it occurs, and then calculate its weight, and then arrange it in ascending order, is it? And then you can build the double tree, and then you can build a Hoffman code, is it? Hoffman code. And then once you have the Hoffman code, how do we do, so the next question is, how do we do encoding and decoding, is it? Encoding and decoding with the Hoffman tree, with the Hoffman coding, is it? Hoffman codes, okay. And here we first, for encoding, we are going to build a Hoffman tree. Hoffman tree, okay. So let's see, suppose we have this code file. We have a code file, okay. So code file, it's made up of letter and its code. And its code, okay. What it looks like is something like this. B, it's 0, 0, all 0, okay. Then C, it's 0, 0, 0, 1, okay. Then D, we have 0, 0, 1, okay. Then we have A, is 0, 1, okay. Then we have E, is 1, okay, E is 1. And so this is a file, plain text file, okay. You have a letter and then its code. You have a letter and its code, okay. So what we can do, how do we build the Hoffman tree, okay. So later on, then you can decode it, use the Hoffman tree, okay. So the way to do it, you can scan, is it? You can scan. And then we start build the root node, okay. And when we build the Hoffman tree, okay, when we build the Hoffman tree, so all intermediate node, nodes, we are not going to use a weight because in the code file, we don't have weights, okay. We just use a star to represent, okay. And for leaf node, then we are going to use its letter. Its letter, okay. So let's see. And we start at the root node. We start to scan. As it's 0, so that means you need to have another. So here it's 0, is it? So you have the root node, and then you're going to 0, is it? And the next one is 0, is it? And then you add a star. It's intermediate. Next one is 0, okay. So I have another 0. Okay, the last one is 0, is it? And now it's the end of the code. So you are going to add letter B at the leaf node. Okay, and then you can start with the second. It's okay, 0, 0, 0. We already have, is it? And it's 1, is it in this case? So you're going to add this new node. Okay, so it's C. Is C? And then let's see D. Okay, D is 0, 0. Is it? And it says next is 1. Is it? And it's the end of the code. So it's D and it's 1. Okay, and then what's next one? It's 0 and 1. And you don't have that branch yet. So you add that branch. And the last one, you go directly to the branch and you add the branch as 1. Is it? So you just read the code and the following. If it's 0, then you go to left. If it's 1, you go to right. Is it? If it doesn't exist, then you add the node. Is it? When it reaches the end, you add that letter. So now we build this Hoffman tree. Okay, so this is a Hoffman tree. Okay, based on this code provided. And as to how to come up with this code, it's what we explained before. Is that you need to calculate the weight, the frequency weight, is that, and then you can come up with all of the codes. Okay, and here we build this Hoffman tree, is it? And once we have this Hoffman tree, and then what the next one is, so this is encoding part. So encoding part, what you're going to do is you're going to build the Hoffman tree. Okay, you're going to build the Hoffman. And then with this Hoffman tree, how do we do decoding? Is it do the decoding? Okay, then let's see this example. So here we have some sequence of code. So we have 1, then we have 0, 1. Okay, then we have 0, 0, 0, 0. Okay, and then we have 0, 0, 0, 1. Okay, and then we have a star. Okay, suppose this is the code, some mysterious message. So some secret message, suppose. Okay, suppose this is a message you receive. Is it? How you recover this message back? You need to want to know it's ABCD so that you can read it. Is it? So how do we do the decoding? How do we do the decoding? So we just read, is it letter, code by code? Is it? So always just like a binary search tree, you always start at root node. Is it? And it's 1, you follow the branch. Is it? You follow the branch, oh, you reach E. Then you know, okay, this is, you can decode it. It's E. Is it? And then you continue, okay. Then you start, okay, it's 0, I start at root node. And then, oh, then I go to 1. Now I go to 1. Is it? Okay, so now I reach at A. Is it? I reach at A, so okay, so this is A. Is it? This is A. Okay, so you decompose. And then next, what you do is, okay, 0, I follow, then another 0, I follow, and then another 0, I follow, then 1. Is it? And I reach the leaf node C. Is it? C. Okay, so now I see, okay, these 4 codes represent C. This represents C. And what next one is the same thing, 0, 0, 0, 1. So you reach another C. And when you see the star, that means the end of the code file. Is it? So now you can decode the code file as EACC. You recover the file back, as it is EACC. Is it? So that's how you do the decoding. Okay, so you can see the encoding and decoding both need to use the same Hoffman tree. Okay, same Hoffman tree. And then you can do encoding and decoding. And for each one, it's also different. That it's not you have a fixed Hoffman tree. Okay, it's based on your article, your paragraph, the frequency of the letters. Okay. Okay, so this is the general idea about, so conceptually, about Hoffman coding. Okay, Hoffman encode and decode. how we build the Hoffman tree and use it to do encoding and decoding. And what next is, then let's take a look at the coding part. How do we do that? Okay, let me see if I get it to the correct. Yeah, I did get it to the correct. Hold on, okay, and also let me find, oh, I need to go to our course website also so that we can see, hold on, okay, let's get to the course website. Binary search tree, okay, the class notes. Okay, later on we will see that. Okay, then next let's take a look at our code. Okay, the code. First, let's take a look how we build the encoding and the decoding, okay, scheme, everything. So over here in this example, we define a class, we call it Hoffman. We call it a Hoffman, okay, within it as just similar as binary, so we have the bin node, okay. And the bin node has data, and it also has left and right, okay, left and be careful, okay, here we don't consider the frequency calculation, okay. Here, the code file, okay, so Hoffman codes already established, okay. Already established, okay. And then it's arranged kind of like you have A as 0, 0, 1, something is B, 0, 0. Okay, something like this, okay, you arrange it. So we are going to have some file look like this. And then you, based on this, then you're going to build the Hoffman tree. Okay, the bin node then have left and right, nothing, and we initiate the constructor, okay, with whatever the data. And similar, we only have a single instance variable called root, okay. And with the Hoffman, the root, we are going to assign it as a star. You remember what we discussed, is it? We don't have weight, we use a star to represent, okay, represent. And then we are going to start to build the decoding tree. So we have a method called build the decoding tree. As it build decoding tree, we are going to use a file, plain text file, as it. And the plain text file over here, we use a scanner, as a scanner. So we are going to read each of the letter, as it each of the letter. And so we associate the plain text file with the scanner. Then we can start to read letter by letter, as it. Anyway, so we are going to do scanner. Scanner selects is get a string, etc. And we are going to do letter by letter, etc. So we get a letter. And if the letter is a star, then you finish, etc. The file is done. Otherwise, you are going to continue, etc. And each time for each of the letter or 0 or 1, you're going to insert it to the Hoffman tree, as a decoding tree. Okay, then let's take a look at the insert, how it works. So for the insert, as it, and you set, so the P is kind of like what we previously learned as a cursor node. As a cursor node, okay. So I always start at root node, as a root node. And then it's based on the length of the code. This is the length of the code. Okay, and for each of the 0, 1, as in each of the 0, 1, And if it is 0, we said if the left doesn't exist, then you're going to build the intermediate node. Is it intermediate node? So intermediate node always has a star, is it? And you let your cursor go to left, is it? Or if it is 1, you go to right, is it? As what we already demonstrated in our drawing. Otherwise, if it's not 0 and 1, it's going to be illegal, is it? Once. And when you finish the code, is it like A0001? Is it? So this is when you finish deal with 0 and 1s, is it? Then you can assign the letter to the leaf node, is it? So the letter will be stored in the leaf node. Okay, so that's how you build the decoding tree, is it? After you build the decoding tree, and how do we decode, is it? So we have a file, is it? And then if you recall what we demonstrated, is that we always start at the root node, and we are going to do letter by letter read, is it? You're going to read letter by letter, and each time you just read a single letter, is it, from the code file, is a code file. And if it is a star, if you record, that means it's the end of the code file. So we finish. And if it's 0, you go to left. If it's 1, you go to right. If it is something else, that means your code file itself, it's wrong, is it? Then in this case, you can also decode, is it, to find all of the corresponding letters for the specific code, okay? So this is the decode. And then in our example, we also print out the tree, okay? We also do the horizontal print out, okay? And over here, it also involves the recursive. So it prints the right tree first, and then print the node, and then print the left. Okay, so that's what, and also horizontally. So that's why the string builder is keep getting all of the so the star or the letter, is it, and keep, and plus the space appending to that string builder. And after you finish it, we'll print out the whole tree, okay? So this is, we also print out, and we can also display the decoding tree, okay? Starting as a root node, is it? And the indentation, of course, initially is 0, is it? And for each level, you add 8. Okay, so this is the Hoffman encoding and decoding. So we group them in a class. And then next, let's see our example here. So here we have 2 code files. Okay, one is both are plain text file. One is a code file, the other is message. So that I will get it clear. Okay, let's see. Go to this. Let's go to our website. So on our website, hold on. Okay, let's first take a look at the code file. Okay, this is what the code, it's a plain text file, you can see, is it? So you have a letter and then it's code, a letter and it's code. Letter, and then that's indicates the end of the file, okay? And let's get back. I need to go to, oh, By the way, can you all see my Canvas course website?
No, Dr. Liu.
Oh, okay, I just explained too. So I need to stop sharing. And then let's get back to our Canvas file. Then share. I just explained. Okay, and our Canvas, our course website, we have the code file and the message file. Okay, and I also have the corresponding Hoffman and its app driver. Okay, and this one, and then next let's get to. Oh, I first needed to clear everything. It's just. Can you all see my code file?
Yes.
Yes.
Oh, okay.
Yes.
So this is the input code file looks. So it has a letter and its code, a letter and its code. Is it? And if you have the star, that means it's the end of the file. Okay. That is what this file looks like. And then let's take a look at the message file. Okay, so here we have this message file. Message is just a bunch of 0 and 1s, is it? And then if you have the asterisk, that means the end of the file. Okay. Okay, so I will stop sharing again and go back to our coding. Okay, so this is the driver part. Okay, so we first read that code file. Okay, so anyway, we are going to create a file object. Is it? Then we create our Hoffman object. We start to build the decoding tree. As I build the decoding, and we display the decoding tree. Okay. So internally, as that you can see, with this code file, you have its corresponding Hoffman tree built, as that built. And then with coming in the message, as that, then you can use that Hoffman object to decode the message, So over here, just be careful, okay? So if you have another code file, a different one, then you need to have a different Hoffman object be created. Okay, then you build its decoding tree. And then when you do decode, you need to call its corresponding one to decode the message. Okay, so for each one of it's a different Hoffman tree, okay? And we can run this and take a quick look. Yeah, if you take a look, is it? So that's what this Hoffman, it's a horizontal, is it? So that's the right tree part, is it? And here you have the left tree part. Is a left tree part. Okay, so this is a Hoffman tree, And with that message, then you can find the corresponding message that is CAB, as a CAB. Okay, so this is all of the information regarding Hoffman tree. Okay, Hoffman tree, and it makes basically it's used. So the key concept for Hoffman tree is it use variable lengths of codes to represent each individual letter. Okay, but requirement we need to be careful is for your Hoffman code, okay, Hoffman code, and don't any of the code shouldn't be the prefix of some other codes. Okay, so we need to when you build the code, you need to be careful about this. And Hoffman coding, we also see it meet the minimize expected code length, as it meet all of those definition. Okay, so one of the binary tree application we kind of see, okay, it's with Hoffman encoding and decoding algorithm. And the last topic in this unit, binary search tree part is how about, because so far all of the examples we see is we use our own binary search tree. We build our own tree and then go ahead to use it. And in Java collection, there is also a data structure and you can use it and for a binary tree, okay? So next we are going to go over with that. So first, hold on, okay, let me find the Java official document, okay, Java 8. Let's get to this website, okay. And I'm going to sharing screen. Okay, so in Java, if you want to use the binary tree, you can also use the class. It's called tree set. Okay, and later, next unit, we are going to learn set and map. Okay, so kind of right now, we just started with the tree part of the concept. Okay, so tree set. Okay, so let's see the tree set. And the basic it says it's some set implement with tree map. Okay, and we can also take a look what the tree map means. Okay, the tree map. And it says the tree map. Later on, we will also learn. So anyway, it's some binary tree. It's tree-based map implementation. Okay, so that's why over here, oh, hold on. I need to take this off. That's why over here, okay, over here, we are going to use the tree set, okay? And set it's anyway, so each, and we already see, okay, in our binary search tree, it's also the same. So each item is unique, okay, unique. Okay, so based on the tree map based on the tree implementation, okay. And here it says the element order using their natural ordering, so comparable interface or comparator, okay. So either is okay. And they also said this implementation provides guaranteed log n time for add, remove, and contain. Okay, and all this add, remove, contains belong to the collection because this is the tree set is also the, if you recall, the collection hierarchy in Java is that it's iterable, is that, and then it has a collection. That so set previously we learned that previously we learned like a list, and the deck is it. Q, is it? Anyway, so those interface, is it? And later on in our unit, we also learn set. It's also some interface, okay? So anyway, the tree set in this hierarchy is some concrete class, okay? And because they are in this hierarchy and the add, remove, contain, they are all supported by collection interface, is it? And if you recall in list, is it in list, whenever you do search, is what? It's order of n. Is it order of n, linear? Is it? And also when you do add and remove, it depends on where you want to add or remove, is it? And it also may be order of n. And if you want to add at the back, of course, so it may be, so it depends on the situation, is it? But anyway, that's for the list, is it, cases. And over here, is that its implementation is guaranteed log 2n, okay? And for binary search tree, is it average time complexity? Is it for searching? Is it for adding? It's log 2n, as previously we discussed. So it's matching, okay? That's just average case, okay? The worst case, it's still linear, okay? So anyway, so we are going to use this tree set, okay? And then let's take a look of a coding, how to use the tree set. I need to find my file, that tree set one. Okay, now I get to the file, so I will restart sharing screen. Sharing screen. Okay. Okay, so we are going to use that tree set. Is it tree set? Okay. So let's take a look. So in order to use the tree set, just like a linked list, okay, array list, you always need to specify the type of the tree, okay? In this case, we are going to have an integer tree, okay, integer binary tree. And then here we have all of our data, okay, from that data file. And then if you take a look, is that we just use a scanner to read number by number. And then, did you see, you just call the tree sets add method. And then all of the number will be stored in this tree as a binary search tree. Okay, it's also, and in this case, it's a red-black tree. Okay, so anyway, it's some binary tree. Okay, so it's not in the order like the linear way. Okay, so all numbers stored in a binary tree. In a binary tree, okay, it's called a tree set. We use Java collections data structure, tree set, okay, and it's pretty convenient, okay, here. And then, because it's belong to the collection, is it a collection? And so collection support iterating as an iterable interface. So here you can also do the iterating. Is it? And you just call it's an iterator, then you can do the has next and next. Is it to do the iteration? Okay. And hold on, let me, first let me clear this. And then how about let's first run this, okay, to see what we get. Did you see, if you take a look here, If you take a look here, as it says tree set using iterator. So here is all of the output. Is it? And arranged in what? In ascending order. In ascending order. So why it is this? It's because of that iterator. Okay, that iterator, it use what? Use in order traversing. Okay, so that's why. And if you recall previously in one of our example, we discussed how do we implement that. As basically you can see in the library, it's also kind of use the concept. Is it? Then next, let's see. I need to get this. How do I bring back my code? The code, where is the file? Let me find it. Okay, so anyway, so you can see it's quite convenient, is it? If you use a tree set and then you use the iterator, then has next and next, you can traverse, okay? But be careful, here it's using that in order traversing. So that's why it's arranged in ascending order. Ascending order, okay. Okay, so that's the idea for this part. And there are quite a number of methods you can use with a tree set. You want to know how many items in this tree, is it? What will be the first item, last item? Okay, and higher, lower, what are this? So 50, that is all the lowest number or greater than 50. Okay, and the highest number less than 50. Okay, so higher it's, so here's a 50. So all the above. Is it lower, it's go to the less than part. Okay, and also both of this doesn't include the number. So basically both of this also return you the range of the number, the range of the number. And then next, let's see the other two methods. You can also call ceiling and floor. Okay, ceiling at 50, so that's going to be lowest not great and including that. So this will be including 50 and all of the number right above it, is it? And the floor is including and less than. Okay, so you can also have the range of the number you want to find. And what is a head set and tail set? Is it? So head set is all numbers before 55. Okay, and the 60 is all of the numbers after 60. And if you want to include or not include, you can use true and false. Okay, you can also specify the range. So you can do subset, as a subset, and include or exclude. You can set true or false. Okay, so all of those methods, you can see it's quite also helpful. Is it? Let's see, we can take a look at the output. Is it? So the output. So the numbers, is it all number before 55? Number 60, is it number before number? So it gave you all of the subsets, is it? And you can also specify the subset, and they can also be listed. Okay. Let's get back to this. And then you can also do delete. Okay, so here it shows. So you, and over here to take whatever number I want to delete, is it? So if the number you can find, then it can be deleted. And after the delete over here, so you can call the delete method, is it? And after that, you can check, you can call the contains to check if that number is deleted or not, is it? So let's get back here, is it? Let's enter some number to delete. Suppose we, let's see over here. We have some number, suppose 61, is it? So let's see. 61, is it? And it says, if you take a look, it says 61 deleted. And then you can call the contain method. Is it? It says 61 is not in the tree. And you can output the tree. You can see 61 is not there anymore. Is it? Okay, so so basically that tree set, so you can also use a tree set if it meets all of your needs, okay? But of course here it doesn't include like the path. And if you do want to get to how to find the path, then there are some other ways you can try to figure out. But anyway, so the tree set provides another option, and you can do some operations with binary search tree, okay? And so we are done with the binary